Let's talk about the gradient function from a graph. Here I've drawn a graph of f of x. We'll call this curve f of x. It goes down and up and down again. And I've drawn certain points along the way. At point A, our derivative is negative. If I draw a tangent line in there, you can see the slope is down. So for x is less than x1, our dy dx is less than 0. We have a negative derivative here. At B, we can see a tangent line would be horizontal, so we say dy dx at this point is equal to 0. The same is true at point D. dy dx is equal to 0. These are called stationary points. A stationary point can be a maximum or a minimum or a stationary point of inflection, which we'll talk about later. At point C, we've got a positive derivative. So we say that when x is between x2 and x1, then our dy dx is positive or greater than 0. And clearly at point E, our derivative is negative again. Our dy dx is less than 0. So we can say that for x greater than, here is x2, our dy dx is less than 0. Notice what's happening. If the function is decreasing as x is increasing, y is decreasing, then I have a negative derivative. If I have a turnaround point, either a minimum or a maximum, then the derivative is 0. At this point here, as my function is increasing, as x increases, y increases, then my derivative is positive. Again, my derivative is 0, and my derivative is negative over there. Here are some examples with the graphical interpretation of the derivative. For example, find f dash of 3 given f of x is equal to x cubed minus 2x squared plus 10. First, we have to find f dash of x. F dash of x is within our power now that we know how the different rules works. The derivative will be 3x squared minus 4x plus 0. We want to find f dash of 3. Well, first we find the general expression for f dash of x, and then we replace x with 3. So it would be 3 parentheses 3 squared minus 4 times 3, which would give us 3 squared is 9 times 3 is 27 minus 12, which is equal to 15. So there's our answer right there. And that is what? That is the derivative at 3. That's the slope of the tangent of this curve at x is equal to 3. Another type of example we might see is this. Find the gradient of the curve, which just means the derivative, the slope of the tangent, with this equation, y is equal to 9x minus 9x cubed. At this point, well, at this point, x is equal to 2. We don't really care about the y coordinate being 10. So first we have to find y prime, which is equal to f dash of x. For this particular equation would be 9 minus 3x squared. And then we want to find f dash of 2, which is 9 minus 3 times 2 squared, which would give us 2 squared is 4 times 3 is 12. 9 minus 12 is negative 3. So there is the slope, or the gradient, of this curve at this point, the x-coordinate being paramount. Here is one more problem with the graphical interpretation of the derivative that I just couldn't resist. Because this is the kind of thing that you're going to be asked to do again and again. Given that f of x is equal to this function, x cubed minus x squared minus x plus 1, find the coordinates of all points for which the curve with the equation y equals f of x, this curve, has a horizontal tangent. Well, that means, first of all, we have to find what the derivative is, because we want to know where the tangent is horizontal. In other words, we want to know where the slope is equal to 0. In other words, we want to know where does f dash of x equal to 0. Well, what does f dash of x equal? That's our first step. F dash of x equals 3x squared minus 2x minus 1. And the derivative of 1 is equal to 0. And we're going to set that derivative equal to 0. Well, when we do that, the first step we'd want to do is try to factor this. And luckily, this does factor into 3x plus 1 and x minus 1, which means 3x plus 1 is equal to 0, so x is equal to negative 1/3. And x minus 1 equals 0, so x is equal to 1. I have my two x coordinates. when I plug these back into my original equation, not into my derivative, but into my original equation, I get the following points. Negative 1/3, 32 over 27, and that's just a bit of basic algebra, and 1, 0. So I get my 2 points. I found my x-coordinates, and I plugged them back in to the original equation. Not the derivative, but the original equation.